Okay, so 822 and I think 823 as well, they have a lot to do with the calculator problem. So going back to chapter 4, regression. We've done regression for lines, but now we're going to do it for curves, essentially, is what we're looking at. So recall Julia's father used dry ice to keep glasses in his restaurant very cold. The dry ice sublimates, which I think just means melt, but I don't know, in the restaurant cooler as shown in the table at the right. So the weight goes down. I don't know, maybe it doesn't. Ask Heflin or Cohen what sublimate means, because I don't know. So anyways, it says recreate the scatter plot and the LSRL of the data. So if we did it in this calculator, you can see I already put the data in. I can go stat, calc, linear regression, and I can calculate it and get the LSRL. The other thing that you can do, and you'll notice I'm ignoring R and R squared and all that stuff for right now at least. We'll see if I have to put that in. If you're using Desmos, same thing. You're just going to make a table. You go here and you make a table and input all the data. And then what I'm going to do is I'm going to go here and I'm going to type this Y1, this little tilde MX1. So I use Y1 because this data is Y1. I use X1 because this data is Y1. For whatever reason, if your table is like X2 and Y2, you would need to put Y2 and X2 here. It doesn't matter. Plus B, and it does it for me. And you can see I have the exact same equation. My slope is negative 0.52. My y-intercept is 15.209. So the math is the same. It doesn't matter if you're using Desmos or the calculator. As far as residuals, though, and I don't know that it's asking us to do the residual plot. I think, yeah, so they want a residual plot. So what I'm going to do here, I'm going to go, and again, hopefully you'll remember this from chapter 4 because I'm going to do it fairly quickly. But, oh, wait a minute. Yeah, I think I got a little bit screwed up. I think I go vars, right? No. Second vars, maybe? Second list? That makes more sense. There's my residuals. So I had to go second list. So it's been a while since I've done this as well. So there we go. There's all my residuals. So I will go up and I will make a plot for this. I will plot L1 and L3 because my residuals are in L3, not in L2. I will graph this. I will go zoom 9 and let the calculator pick for me. And so you can see I see a little bit of a pattern there for sure. So I would say that a line, it does not seem like a good fit. That's what the residual plot tells us. And again, if I want to do this in Desmos, I can go over here. Well, pretty easy. I just click plot. You see where it says residuals? And there's R and R squared, all that stuff there for Desmos automatically. I go plot, and you can see it's down here. I'm going to get rid of this, and I'm going to focus in on my residuals. And yeah, it doesn't look fabulous right there. You can see it starts up and goes down. But what I could do is I could change my y-axis to go from -1 to +1. Oh, shoot. I did the x-axis. Whoops. Anyways, I could make the y-axis go from -1 to +1. And I think that looks a little bit more clear that you see that distinct sort of same way. You get that same residual plot with the same thing telling us that there is a pattern, so a line is not a great fit. So what would be a good fit? Well, what we could do is we could run a exponential model instead of a linear model to see. So let's go ahead and let's do that instead. So we will go stat, calc, and you can see we have all these other different kinds of equations here. But if I go down to 0, I get exponential regression. So I'm going to use L1 and L2 again, and I'll calculate it. I'm not going to worry too much about the graph because you're going to see it in Desmos anyways. And I get this equation, 15.37 with a multiplier of 0.95. So we get that decrease. You can see it's going downhill. And that is what we're going to use. We're going to go over to Desmos. And again, I will say y1 equals a times b to the x1. I need that to be an exponent to the x1. Oh, shoot, I wasn't supposed to put equal, was I? I was supposed to use that tilde, so let's go ahead and put that tilde in right there. So there we go. And you can see I get the same equation either way. My A is 15.37, my B is 0.95. And if I want to graph that, I can go ahead and I can graph that equation. So you can see that my curve does a pretty decent job of hitting those points. Again, that was the line that I have previously. And again, you could get the same thing over in this calculator if I put it in. I just think it's easier to sort of leave it in Desmos. I just wanted to let you to see either one. But what I could do is I could plot the residuals and sort of zoom in and see, and they bounce around a little bit more. So that looks pretty good. By the way, the R and the R squared we're not going to worry about too much when we do exponential curves. We're going to worry more about the fit and the residual plot. Again, the R and the R squared are going to be something totally different, so we're not going to worry about those too much. But it looks like maybe that would be a better fit for that. And you can see up here, if I go into my table, there's the residuals for the curve. So that E2 is right here. So kind of interesting. E1 residuals are right there. There's those residuals versus these residuals. And these ones seem to bounce around a little bit more. It goes up, down, and back up. So not necessarily just down and up. And so simple. So that's where we're at. Now, when we go to the next one, and I think what I'm going to probably do is pause the video for a second. I think that would make the most sense. I'm going to go 822B, and it says below is a list of amounts of oil produced from 1905 to 1972. MMBL stands for millions of barrels, so this is millions of barrels, and this is the year. By the way, I want you to see this is the year, and then it jumps up, this is the year. So columns 1 and 3 are the same column, and columns 2 and 4 are the same column. It gives me some checksum. So I'm going to pause the video, and I will put this data in. I think I'm just going to put it in Desmos, honestly. I think we've done enough with this calculator that if you have one of these calculators, you can definitely use these things. It should make sense. The only real difference is from what we've done. Again, you're going to go stat edit and put the data in L1 and L2. Is when you run the regression on this, you're going to go calculator. Instead of putting linear regression, you're going to go down and you're going to put exponential regression. But my suspicion is that if anyone's going to be doing this at home ever, you're probably going to be using Desmos and not a calculator or a simulator. So I think I'm going to pause this and put this data in Desmos. Desmos, and I put this data in. A couple of points I want to make. First of all is we're not putting 1905 and 1910 because of course that wouldn't add up to 792. We're actually putting 5, 10, 15, 20. So year 1900 counts as year 0. The other thing I want to point out is this. It goes by 5s, and then once you get to 1960 it starts going by 2s. So that's just worth considering if you're putting this data in yourself. So when I go over to Desmos, I have all this data put in. If I go back and zoom way out, I'm gonna get that data. Actually, let me go ahead and get rid of this here. So you can see that's that data. So it looks really weird here. If you want it to look better, my suggestion would be to change the x-axis to go from something like 0 to I don't know, like maybe 100, I guess. And that's going to give you a way cleaner look at what that data actually looks like, I think. Even then it begins to start to get a little bit screwed up there. So if you want a real clean look, it looks like it goes to 20,000. So make your X go from 0 to 100 and make your Y go from 0 to 20,000. And again, I could set this up beforehand, but part of this is just to show you guys kind of how you can manipulate Desmos if you're not familiar with it anyway. So now we get a nice clean look at that. I think that looks really good. And I don't know, does that look linear? I would say no. If I draw a line through it, that doesn't seem to do a great job, but if I draw a curve through it, that seems to do a lot better job. And then of course from there, I can plot those residuals. And again, those residuals plot up right here, but I think it would make a little bit more sense to kind of try and zoom up on there. It looks like it goes to, what are these going by 400, so I don't know, maybe 1,000. I don't know, did I put the wrong data in somewhere or something? I don't know. But that seems to kind of look a little bit funky. Let me go ahead and check this data again and see if I screwed up the data. So no, the data's fine. I think what's really thrown me is the fact that this one is such a big miss because the data was the same for these two right here, that it really pulls everything down. So you can see most of the residuals missed high and not low, but I guess there is no distinct pattern. It still sort of bounces around. I think that one outlier kind of screws it up a little bit, but not really noticing a pattern. It just, like I said, kind of threw me a little bit for a second, I think, right there. All right, so as we continue along with this, then I'm going to close this out and we will go to problem 8105. So let's go ahead and open this and jump back to problem 8105. So 8105 says, according to your exponential model from the previous problem, how much oil was produced in 1996? So what we would do is we would go over here and we would plug 96 into this equation, right? So we plug 96 into this equation, or we could just go to 96, which is, what, 96 is way up here. And we could see roughly where we end up at 96, and you could see it's like 114,000 million barrels. So let's remember that, 114,000. And then it gives us the actual. Below is a continuation of the data for the oil production. Compare your prediction for 1996 to the amount given in the table. Well, it's not even close. We predicted way more. So why was it so far off? Well, I mean, a lot of things have changed, you know. Oil dependency apparently is going down. You can see it from 74 to 96, it didn't really grow that much, not like it grew previously in this table. So, you know, I don't know, maybe solar, maybe gas, fuel efficiency. Cars are way more fuel efficient than they were. I don't really believe public transportation is that much more popular, but who knows, maybe I'm wrong. But those can be some of the reasons that our prediction was so far off. All right, so it says add this data to the previous data in your calculator, and then let's look at that scatter plot. So what I'll do here is I will pause this and add this data as well. Okay, so I have that data in, and you'll notice it looks really funky. And again, I changed this from 0 to 100 and from 0 to 25,000 to get a nice look at it. If I go with the exponential, you can see what it looks like. Now if I go with the residual plot, if I go to the residual plot, you can see the residual plot looks crazy. Definite pattern for sure. So, like, what's going on here? And the book makes some suggestion for us. What they really are thinking might not be a bad idea is, what if we have a curve for this data and a line for this data? So it wants us to run just the data from 82 to 96 and see what that looks like. So again, I'll pause and set that up. Okay, so here's the data from 82 to 96. That's all I have is 82 to 96. I got rid of the rest of it. And the question would be, what would be a better look at this? Would it be a... I don't understand why I lost these curves. Let me pause this again and see what's going on. All right. Well, I apologize. Apparently, it didn't like, I deleted all the other data. It didn't like having all those blank spots there. So now I just have this data here. And what it's basically saying is, all right, do we still like this as a curve, or do we like this better as a line? That's the real question. So if I have it as a line and I plot the residuals, you can see that my residual plot kind of bounces around pretty good. I like that. What if I look at it as a curve? What does my residual plot show me? and the residual plot's real similar. So kind of, I think what I'm looking at here is that since the curve is so close to a line anyway, right? The curve looks just like the line does in that data, that I think it switches to linear. So it's kind of interesting. The book is trying to make the point that at the beginning, the exponential curve is a better fit, but then the line becomes a better fit. So it's almost one of those step functions where the book wants us to do a curve to start with and then switch over to a line after that. So it's saying, hey, now let's look at our 1992 prediction. And if you'll remember, our 1992 prediction was way off. We predict like 140 something thousand. Well, now what does our 1992 predict? So I'm going to go ahead and look at this as a line, and my 92 ends up predicting about 22,000. And if we go over to that data and 22,000 is a pretty good fit. So again, and just to, I'm not sure how clear I'm being here, it essentially wants us to make a piecewise. We're going from a curve until about 92, and then 92 to 96 we're going to switch over to a line. So this one would have, there's two pieces of this, a piecewise function. Piece 1 would have an exponential equation, and piece 2 would have a linear equation. And that's something we're allowed to do, right? We're allowed to say, hey, use the curve till 92, and 92 after, switch it over to a line. And again, I think that's what makes this an advanced class, is the concept that these are decisions that you're allowed to make if the data doesn't make a lot of sense. I know it's a little bit kind of interesting and weird to think about, but it makes a lot more sense to do the data that way. So it says, since you use two different models for the data, you will need to make a piecewise graph that shows both models. On your paper, make a scatter plot of oil production data with a piecewise model. Create a scatter plot with the oil production from 1905 to 1996 with both the exponential best fit model and the linear best fit model shown, and then have the domain. And again, the domain here would go from 0 to, it was 82, or 1900 to 1982, and the domain here, or 1992, I'm sorry, and then the domain here would be 1992 up. Or was it 82? I'm getting confused now. I guess it was 82 to 96, but yeah, I'm sorry. So 0 to 82, and then 82 to 96 would be the domain, and this would be that curved equation, which I don't have anymore, and this would be the linear equation, which I guess I do have. The linear equation would be right here, 2.92x minus 4695 is the y-intercept. At that, let's go ahead. I know this is a lot going on in this lesson. I had to pause and restart it a bunch of times, but let's go ahead and finish this thing off and see where we're at here. So we will go 822D. It says, remember the problem 881, where Mitchell wondered if he could write the equation of an exponential function that passed through points 2, 1, 44, and 6, 7, 29, which we've already done. He solved the system of y equals a times b to the x equations. Mitchell determined the equation y equals 64 times 1.5 to the x, which hopefully you remember that's what we got. Mitchell had another idea. He wondered if he could use regression functions on his graphing calculator to determine the equation of the function, exponential function. What does Mitchell mean? So this is kind of cool. I actually do this one in the calculator. If you wanted to, you could definitely do this one. Actually, this is an easier way for me to clear it, just turning it on and off. If you want to use this one in Desmos, you can, but I'm going to do this one here. So I'm going to go stat, edit. I have 0.2 and 0.6, so 2, 144. And 6, 729. And what they're saying is, hey, look, I'm going to run this as a curve. I'm going to go stat, calc, exponential. All I need is 2 points, and I can draw a curve through those 2 points. And it will give me the equation, 64 times 1.5 to the x. So pretty simple if we have one of these calculators to get that equation. It says, does Mitchell's method work for determining linear equations as well? Well, yeah, we have these two equations. Right? I'm sorry, we still have these 2 points. So instead of an exponential equation, let's go ahead and have it draw a linear equation instead. So we're going to go here and it will give us the linear equation instead. So you can see we can either have it draw a line through 2 points, which we did on this one, and we got this equation, or we can have it draw a curve through 2 points, which we did just a minute ago. So kind of neat. These calculators definitely save us some time. Again, that'll work the exact same in Desmos. So I feel like this video has been 100 hours long. It's taken me a long time to make it, just putting all that data in. So hopefully it hasn't taken you as long to watch it. Let's see. All right, have a good one.